Right now, you're being pulled. You feel it constantly, but most of the time you don't notice it. It's the weight in your body, the pressure of your chair against you, the heaviness in your feet. Gravity is pressing you toward the earth every single second. If I asked you, what is gravity? Your first answer would probably be simple. It's the force that pulls things down. That answer is so intuitive, so obviously correct from moment to moment, that it shaped our understanding of the universe for 300 years. And it's still the right way to think about gravity in almost every practical situation. But here's where it gets interesting. When physicists describe gravity more completely, they describe it differently. Not better, not incorrectly, differently. And that difference reveals something profound about how we understand reality. So today we're going to explore that gap. Because understanding it doesn't mean gravity becomes less real. It means you'll see how deeply it's woven into the fabric of the universe. Let's start with what you actually feel. Stand up for a moment, if you can. Feel your weight pressing down. Feel the ground pushing back up against your feet. You experience this as a tension, a pull downward, a push upward, and they balance each other out so you stay still. Now imagine yourself in an elevator. As it starts moving upward, you feel heavier. The pressure increases. As it reaches the top and begins to slow down, you feel lighter. For just a moment, if it's a smooth, quick stop, you might feel almost weightless. This is all gravity, right? The force pulling you down. But here's something worth noticing. When that elevator is moving upward at a constant speed, gravity hasn't changed. The Earth hasn't gotten stronger. You feel perfectly normal. But when it accelerates, when it's changing speed, suddenly you feel different. This little quirk will matter soon. Hold that thought. Now let's think about what you're actually experiencing when you feel your weight. Your feet are being pushed up by the ground. The ground is solid. It's not gravity you're directly feeling, it's the reaction to gravity. It's the push of matter against matter. But we describe this whole situation as gravity being a force that pulls downward. And that description works. It lets us predict what will happen. It lets us build buildings and throw balls and launch rockets. So far, everything makes sense. Gravity is a force. It pulls things down. What could be simpler? This is essentially how Isaac Newton thought about gravity, starting in the 1680s. He observed that things fall. He observed that planets orbit the sun. He observed that the moon orbits the Earth. And he noticed something remarkable. The same mathematical relationship described all of these things. There must be a force, Newton reasoned, that acts between all masses. The strength of this force depends on how massive the objects are and how far apart they are. The bigger and closer they are, the stronger the pull. He called this gravitational force, and he wrapped it into a mathematical equation that was stunningly successful. You can use Newton's law of gravity to predict the orbit of planets, to calculate how fast a ball falls, to design bridges and dams and everything in between. And here's the important part. Newton's description is not wrong. It's still taught. It's still used. Every engineer uses it. Every architect uses it. NASA uses it to plan space missions. Newton's picture is, gravity is a force. It acts through empty space. It instantly pulls objects toward each other based on their mass. This was brilliant. It worked. It worked so well that people accepted it as truth for over 200 years. But by the late 1800s, something odd was happening. There was a small problem with Mercury's orbit. Its position didn't quite match Newton's predictions. The discrepancy was tiny, a few seconds of arc per century. Most people didn't even notice. But it was there. A few other puzzles were accumulating too. Questions about light. Questions about how forces could act across empty space instantaneously. Nothing catastrophic, but little hints that maybe the full picture was more complex. Then, in 1915, Albert Einstein published a completely different way of thinking about gravity. And I want to be really clear about what happened here. Einstein wasn't saying Newton was wrong. He was saying Newton was describing something real, but not the whole story. Here's Einstein's insight, and it's genuinely strange. What if gravity isn't a force at all? What if what we call gravity is actually something about the shape of space and time itself? Imagine space and time as a kind of fabric. Massive objects don't pull on each other through empty space. Instead, they curve the fabric around them. And when other objects move through that curved fabric, they follow the curved paths naturally. This is Einstein's general relativity, and it sounds completely wild. But let me give you an analogy that might help. Imagine a rubber sheet stretched flat. Now place a heavy ball in the middle of it. The ball curves the sheet downward, creating a dip. Now roll a smaller ball near the dip. The smaller ball doesn't get pulled by the heavy ball. It simply rolls down the curve in the sheet. It follows the curved path. That's the idea. Objects don't get pulled by gravity. They follow the curved paths through space and time created by massive objects. Now, here's the crucial thing. Mathematically, Einstein's description and Newton's description give almost exactly the same predictions in most situations. They agree about how fast things fall. They agree about planetary orbits. They agree about the motion of the moon. But they disagree in extreme situations. Near a black hole, near the surface of a neutron star, in the intense gravitational field around a massive object, there, Einstein's prediction is correct and Newton's is wrong. And in one small case, like Mercury's orbit, Einstein's prediction matched the observation and Newton's didn't. So which one is right? Is gravity a force or is it the shape of space? This is where it gets genuinely interesting because the answer is, they're both real descriptions and they work in different ways. Let's think about what gravity is a force means. When you use Newton's equations, you're treating gravity as an invisible pull between masses. You plug in the masses and the distance, and you get out a number that tells you how strong the pull is. And then you use that to predict motion. Does this work? Absolutely. Every time you drop something, it falls according to Newton's law. Every rocket launch, every satellite mission, every calculation of planetary motion, Newton's gravity works. But what does gravity is really the shape of space mean? Einstein's equations describe space and time as woven together into a geometric structure called spacetime. Massive objects curve this spacetime. Other objects follow the curved paths. Does this work? Absolutely. It explains Mercury's orbit. It predicts black holes. It describes gravity in extreme situations where Newton fails. But here's the thing. Both of these are mathematical descriptions. They're models. They're ways of organizing our observations and making predictions. The question, is gravity really a force, is a bit like asking, is light really a wave or really a particle? The answer is, it depends on how you look at it, what experiment you do, what precision you need. At everyday scales, thinking of gravity as a force is practical and useful. You don't need Einstein's full description to throw a baseball or build a house. At cosmic scales, near massive objects, you need Einstein's description because it matches reality more precisely. But both are real. Both describe something true about how the universe works. Now, I want to address something important because there's a lot of confusion here. When physicists say gravity is not a force, they don't mean gravity is fake. They don't mean you're not actually being pulled toward the Earth. They don't mean the ground isn't pushing you up. What they mean is, gravity is not the kind of thing that reaches across empty space and pulls on objects. The mechanism is different. The mechanism is curvature of spacetime. But the effect is real. When you drop a ball, it falls. That's real. When you stand, the ground supports you against this effect. That's real. The confusion comes from the word force. In everyday language, a force is a push or a pull. And gravity feels like a pull. Your weight is a very real sensation. But in physics, a force is something more specific. It's something that causes acceleration, that changes an object's motion. And here's where it gets subtle. In Einstein's picture, gravity doesn't cause acceleration. Objects are always moving in straight lines through spacetime. But spacetime itself is curved, so those straight lines appear curved to us. This is genuinely hard to wrap your head around. But the key insight is this. Whether you think of gravity as a force or as curvature, the predictions are almost identical. The difference only shows up in extreme situations. So why does this matter? Why do physicists care whether gravity is really a force or really curvature? The answer is that the description you use shapes what you can discover next. Newton's description worked brilliantly for 200 years. But it eventually hit a wall. It couldn't explain Mercury's orbit. It couldn't predict black holes. It couldn't explain why light bends around massive objects. Einstein's description, by contrast, naturally explains all of these things. It opened up new questions. It led to the prediction of gravitational waves, ripples in space-time itself, which weren't experimentally confirmed until 2015. So the shift from gravity is a force to gravity is space-time curvature wasn't about correcting an error. It was about developing a deeper, more complete description. And here's something crucial: Newton's description still works. We still use it. When NASA calculates trajectories, they use Newton. It's simpler, faster, and accurate enough for those purposes. But when we need to understand gravity at its most fundamental level, when we need to ask questions about black holes or the birth of the universe, we use Einstein. Both descriptions are real. They just operate at different levels of completeness. Think about it this way. Imagine describing a table. At everyday scales, you'd say it's solid. You can put things on it. It supports weight. But at the atomic scale, a table is mostly empty space. Atoms are tiny nuclei surrounded by vast clouds of electrons. The table isn't solid at all. Are both descriptions true? The everyday description works for everyday purposes. The atomic description is more fundamental, but you don't need it to use a table effectively. The same is true for gravity. Newton's description is everyday scale gravity. It works. It's useful. It's true in the sense that it accurately describes what happens. Einstein's description is deeper. It explains why gravity works the way it does. It's more complete. And neither of them is the final answer. Right now, physicists are working on theories that combine Einstein's gravity with quantum mechanics. At that level, gravity might be described in yet another way. But that doesn't mean the previous descriptions were false. It means we're building a progressively more complete picture. So let's come back to where we started. You're standing. You feel your weight. Gravity is pulling you down. That's true. You're experiencing something real. But when a physicist asks, "What is gravity?" they're asking something more subtle. They're asking, what is the mechanism? How does it work? What is its deepest nature? And the answer is, it's more complicated than just a force pulling things down. It's a curvature of the space and time around massive objects. It's a fundamental feature of the structure of the universe. Does this mean your everyday experience is wrong? Does it mean Newton was wrong? It means we've developed a more complete way of understanding something that was already partially understood. This is how science actually works. It's not a march toward absolute truth where each new discovery throws out the old one. It's a spiral of understanding where each new description includes the previous one and adds more depth. And here's what I find most fascinating about this. Gravity, whether you think of it as a force or as curvature, reveals something profound about reality. Masses shape their surroundings. They don't act from a distance through mysterious forces. They curve the very fabric of existence around them, and everything else responds to that curvature. You're sitting here on this planet, moving along a curved path through space-time. You're not being pulled. You're following the curve. And that curve was created by the massive Earth beneath you and the massive sun in the sky. Every moment of your life, you're immersed in gravity. Not as an invisible force, but as the structure of space itself around you. And whether we call that a force or a curvature is almost beside the point. What matters is that we're learning, step by step, to understand the universe more deeply. Gravity is real. How we describe it evolves. And both those things can be true at the same time. The next time you feel your weight, when you experience that sense of being pulled downward, think about what's actually happening. You're experiencing the structure of space-time around a massive planet. You're part of a universe that's far stranger and far more beautiful than everyday intuition suggests. And that's worth paying attention to.